Alright, this is lesson 5.3 based on section 4.8 if you wanted to look in the textbook by Weiss. And we, in this section, will be talking about determining the number of possible outcomes using basic counting rule, combination rule, and permutations. So, these notes are already filled out for us. We often need to determine the number of ways something can happen. Sometimes listing all possible outcomes is laborsome. It would take a long time to write out all the different possible, in this case, license plates that you could have in this state that would consist of 3 letters followed by 3 digits. So, it is important to know how many there would be. Make sure we can account for every person that needs a license tag. So, in order to do that, we need to figure out, first writing out, what I like to do is write out little underscores there. And then I'd like to indicate what are the possible number of letters that I have to choose from? Well, 26, because there's 26 letters in the alphabet. Since we can repeat letters, we'll have 26 for each one of these first 3 slots. I don't fill in the actual letters. I just think about what is the possible number of values that could go there. And then for digits, each one of these spots represents one of these 3 digits. And so that would be 10 digits. So if you think of 0 as a digit, as well as 1 through 9, that's 10 different digits. And then the question is, what do you do with those numbers? Well, we took a look at an example of a smaller example. This is a great test-taking strategy to just solve a simpler problem. So if I have 2 pairs to choose from, a black pair and a tan pair, 2 pairs of pants to choose from, jeans or khakis, and 3 shirts to choose from, purple, red, and chartreuse. I can make a tree diagram here, BT, so my shoes matched with, well, either jeans or khakis with tan, and then each of the 3 different shirt options. And as you can see, we can count these up and get 12, which helps reveal to us that the way we could do this simply is to multiply each of these numbers together to get the total number of possible outcomes. So we will do that use that same principle in this question by multiplying each of these values and get 17,576,000. The next example is similar, license plates. Same as above, except in this case there are no repeats allowed. So in this situation, instead of having our 26, 26, 26, we're going to have 26, 25, 24 times 10 times 9 times 8. And in that we get 11,232,000. Did I say 11,232,000? In this next example, you can see we've got different options for home models, which is interesting to think about. If you get an apartment in college, there's different options to choose from. This is more likely real world situation past college, though, in a apartment neighborhood or a neighborhood of homes. So with 4 different possible styles of homes, 4 different models, and 3 different elevations. The question is, how many choices are there to choose from for your next home? Starting out again, we would draw a tree diagram here representing each one of my 3 models, and then each model paired with a different elevation. So I could have a Shalimar house at elevation A, B, or C. And I could indicate that outcome with SA, SB, and SC. Okay, and so we did that for all of these different possible models and elevations. And you can see we listed these out, which we could also list out here. And this is called a sample space. That's a key term. And ultimately, we could count these, we could multiply, and we have 12 possible outcomes. Next up, we have a different counting rule. So this section is all about counting rules. That first one was all about the basic counting rule. The ones coming up are called permutations and combinations. So factorials are part of the formulas for both combinations and permutations. So let's define those now. A factorial is a symbol in math that looks like an exclamation point. And it simply means to take a number, any number, and multiply it by every number leading up to that number, or every number behind it, as one student said. So if I multiplied k times the number right before it, minus 1, and times every number down all the way to 2 times 1. So examples are always helpful for us to picture it. So it's 5 factorial, but it would be equal to 5 times 4 times 3 times 2 times 1, which is 120. A key part to this is if you ever run across 0 factorial or 0 options, then that's always equal to 1. So that's a key definition. Permutations. So the definition here, it's critical to know. A permutation of R objects from a collection of M objects is any ordered arrangement of R of the M objects. Ordered is emphasized here because later we'll talk about combinations, which are not ordered. Order does not matter. So the number of possible permutations of R objects that can be formed from a collection of M objects is denoted. We cross this out because the font didn't work out very well to correctly represent the notation. We should actually have a subscript of M, a capital P, and a subscript of a lowercase r. And that is, we read that as M permute R. Here's the arrangement of letters, an example. We're going to consider the collection of objects consisting of 5 letters. Here they are, 5 letters to choose from. Total of 5 letters. We want to list all the possible permutations of 3 of those letters. So we want to choose 3 of them and see how many ways we could arrange them, with order mattering. You can see this table has already listed all those out for you, which is nice because question part A says list them all out. So we did that. It's done for us. So then question B just says, okay, count those. Count the ones that you listed out, and if we do 6 columns, 10 rows, it's 60. So practice writing our 5 permute 3, and we get 60. And then part C says use the BCR, use the basic counting rule to determine the number of possible permutations. Well, in this case, we can write out our little slots here for each of the different values that would go for our permutation, and the first one has 5 possibilities. I could put A, B, C, or D, or E in this first spot, followed by, then if I've put 1 here, I have 4 left to choose from, and then 3 left to choose from. Multiplying those together, I get 60. So different ways to get the same outcome. And then there is the permutation formula. And this actually makes things really simple once you're working with larger numbers. So the definition here, you've written this down on your vocab. It says the number of possible permutations of R objects, that would be your sample size, from a collection of M objects. So M is your total. It's good to make sure you know which one is which. So the formula, MPR, is M factorial divided by the quantity M minus R factorial. So let's take a look at an example. We have this scenario of betting at the racetracks called exacta wagering. You have the opportunity in this scenario to pick 2 horses and then choose which ones you think will finish first and second in a specified order. Your questions here clearly indicate that this is a permutation where order matters. For a race with 12 entrants, determine the number of possible exacta wagers. So to do this, we could write it out. First of all, identify what M is, what R is. We have 12 horses, so that's our total. And we have 2 slots to fill, the first place person, or the first place horse and the second place horse. Then we write out 12, permute 2. Plug it into that formula above. So 12 factorial divided by 12 minus 2 factorial, which is 12 factorial divided by 10 factorial. And when you write these all out, 12 times 11 times 10 times 9, all the way down to 1, over 10 times 9 times 8, all the way down, you can recognize that this quantity from 10 all the way down, or 10 factorial, is the same on the numerator and denominator. To simplify fractions, we cancel out common factors. So what's left is just 12 times 11, which is 132. There's a way to do this on your calculators. So if you go into your math menu, the math menu is located right here underneath the alpha button. So type math and you'll see a list of possible menus. We go over to prob, scroll down to 4. There's the factorial button. But let's go back up here to this one, NPR. I know we have MPR here and NPR here, but they actually are both indicating the sample size. So we enter that in. 12 for our M value, 2 for our R value, and again we get that 132. I'm going to skip on down here to combinations, and combinations unordered. It's going to be very important that you can distinguish those 2 terms. A much smaller box for the same example that was given for permutations, because combinations, ABC, is the same as if you had CBA or BCA. And there's actually, if you look back at our first example, this whole column represents ABC, but it's written in different ways because order matters in a permutation. So in this case, if we count all these up, it would make sense then that we have 10, because each one of these in the top row is all we need, which there were 10. Because each column is just a rearrangement of the top one. So, counting these up, we get 10. Now the note says, which I think is super important to point out, if I just had 3 letters, A, B, and C, and I asked you to permute A, B, and C, well, that would be 3 spots times 2, or 3 options times 2 options times 1 option, or 6 different ways to rearrange these letters. Again, just as we see written out here. So the difference between the 60 on the first page and the 10 here is a factor of 6, or 60 divided by 10. Or sorry, 60 divided by 6 is 10. So you see we have to divide out that number of possible ways to rearrange the letters. And that's what you see here in this combinations rule. In the combinations rule, it's very much the same as the permutations rule, only dividing out the R factorial. Here's an example. You can see we have the CD Club, and in the CD Club you can choose from 69 CDs. In the end, after you buy 1 CD, you get 4 free CDs. So the question's asking us to identify how many possible how many possibilities does a new member have for the selection of 4 free CDs. And to do that, first identify your M. There's 69 total CDs to choose from, with 4 that you get to choose in your sample. So we write that as 69 choose 4. We fill it into the formula, 69 factorial divided by 4 factorial. factorial times 69 minus 4 factorial. Or 69 factorial divided by 4 factorial times 65 factorial, which is 864,501. And again, if I wanted to do this in my graphing calculator, I go to the math key, scroll over to the prob, and then scroll down to NCR. And I can type in 69 and 4, and there you have it. Here are the steps to doing permutations and combinations. Divide if order matters. Or sorry, decide. You will divide, but decide if order matters. Rewrite the problem using combination or permutation notation. Write out the appropriate equation, and then use your calculator to help. This may feel unnecessary because you have your calculator. However, it is valuable for you to be able to identify the correct formula for these types of problems.